So in the previous session, we talked about the offsets. Then we talked about offset management, and we saw that Kafka itself maintains. I mean, Kafka itself does the offset management by default by committing the offset to Kafka itself. But with that, we can only achieve at least once the semantics. Now, if at all we want to do the offset management by ourselves, so these are the steps we need to follow for at least once the semantics. So if we want to do at least one semantics, which is already taken care by default by Kafka, but still if you want to do by yourself, first we read the data from Kafka, process data and save that process data to some external storage like Cassandra or some other HBase or Kafka itself or Elasticsearch, anywhere we can save it. Here I'm talking about any consumer. It could be Spark also. I mean, if I take for example Spark reads data from Kafka, Spark processes the data and saves data to some external storage like Cassandra or HBase or anything. And finally the code must be returned to commit the offset. So this is the things we have to follow. So if you see here, let's say we have read up to 100 messages. I mean, probably in some few requests we have read 100 messages. So our next offset request will be your next request will be some let's say sensor topic, zeroth partition. The next request will be offset 100. Again, you after getting this data, we process that data and we save that data. Then we commit the offset. We commit the offset. So again, offset commitment is done. Again, next request you send. Let's say for this request you got 20 messages. You got 20 messages, hence the next request that you will be sending is sensor 0120. And then you will commit the you for this you get the messages, you process that message and save to Cassandra or some external storage. After that you commit offset. Here we are doing manual commit and we say offset commit is 120, and so on will be keep on doing here. Now it may happen that after processing the data and saving the data to HBase or Cassandra, you crash after the second step. Your application, your Spark application may crash after processing the data. Since after processing the data it crashed, it was not able to commit. Let's say the next request that it went is for this it received 40 messages. Sensor 0160 is the next offset request that will go. Now it processed this data. It processed this data. it got the offset from here. I think I am doing something wrong here. Something wrong. Sorry. It's my mistake. So we send the request 100. I mean to say from offset 100 we want the messages. We got 20 messages, means 120 is the offset. We process these 20 messages, then commit saying we have received up till offset 120. Commit 120. Similarly, after we next we will send the offset as 120. We receive 40 messages, process 40 messages, and then we say that we commit offset as 160, because this is how we will do. Similarly, in the next request we'll say we want messages from 160 offset, because we have already processed up till 160. So let's say this request fetched around again 30 messages. Because of this request, so we process, I mean, up till 190 offset we were able to read. Spark was able to read up till 190 offset. So process 30 messages. So before it could commit, as I said, processing was done. Before it could commit, we crashed. The Spark crashed here. So since it's crashed, it was not able to commit that 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 it has processed and saved the messages up till offset 190. So it's already processed and saved the messages up till 190 offset, but it was not able to commit that. The latest offset it was not able to commit, as some because of some reason it crashed. So after rebooting, Spark streaming, what will happen? The next request that it will send is it will see that the latest offset commit was 160. Latest offset commit was 160, hence it will start sending. The next request that will again go is 160. So the last 30 messages are being read once again. So we are getting a duplicate of the last 30 messages. So that's nothing but our at least once semantics. So if you write your code in this fashion, you process the data and save the data first, and then you write the code to commit the offset. So there you will get at least once semantics. So here we are assuming that we are committing offset to Kafka. Something like this. We have Kafka, we have Spark, let's say we have Cassandra, So we read the data, we process and save, then we commit offset here. So this is step one. After that you have this code. After that you have this piece of code. So you manually do this, so it will result in at least one semantics. So I hope the at least one semantics was clear. You have to write the code in this fashion. Your offset commitment should be done later, at the end, after the processing has been done. Only then you can achieve at least one semantics in which there will be no data loss, but there will be a duplicate messages whenever there is a failure. Whenever there is a failure and you restart your Spark streaming application, there will be duplicate records. Now, how do we achieve at most once semantics? Read data from Kafka. After reading, write the code to commit offset. Then process received data and save to external storage like Cassandra or HBase or any other. So if you follow this pattern, first you read the data, you write the code to read the data, then you write the code to commit the offset, then you write the code to to process your data and save the processed data to Cassandra. So in this case, you will achieve at most one semantics. We know that at most once means the data will be lost here. Zero or once you will read. Once is for correct, but if you don't read the data, we can think it is as good as we are losing that piece of data. So it's similar to this. If you see our first request, let's say up till 100 messages we have read. So our next request goes sensor partition 0 and from offset 100. So let's say for this offset, from this offset we got some 40 messages. So we will commit the offset first, commit offset to Kafka. So we will say that we have received up to 140 offset, commit 140, then process 40 messages and save. So the next request that will go is again sensor 0 140. This is the because we have already processed 40 messages. So the next offset request that will go from the consumer to the broker is 140. Again, let's say for this from this offset, we again got some 50 messages, meaning up to 190. So we commit offset saying that we have received the messages up till 190. and then again process 50 messages and save. So the next request that will go is sensor 0, offset will be 190. So let's say for this again we got some 50 messages. So we say that we commit, so it is 190, right? So let's say we got 50 messages, meaning so we have received messages up to offset 240. So we say commit 240. So and while processing our data and saving our data, we crashed. Something happened. Our application crashed. Our Spark application crashed. So we were not able to process process last 50 messages. That is from 190 offset to 240 offset. So these messages, I mean, not, it could be few messages could have been processed and saved, but not all the messages are being processed and saved. Somewhere in between, or just assume that none of these messages were processed, just it crashed there. But we have already committed, saying that we have already read 240 messages. Now we restart our Spark application, Spark streaming. Because it has crashed, we have to restart it. Now the next request, as soon as it restarts, it will check what was the last commit offset. What was the last commit offset? The last commit offset was 240. Hence, it will start sending the request from offset 240. So obviously, we lost these 50 messages because these messages were never processed and these messages were never saved to some external storage. So lost we lost last 50 messages. So which gives you the at most once semantics. I mean, I'm not sure what is the use case. Some use case may be there where it is okay to get some duplicate data. I mean, it's but we it is okay to receive, it's okay to lose some messages, but you don't want some duplicate data. So that is nothing but at most one semantic. So if you write your code in this fashion, first you commit and then you process the data. Yeah, here is a question. The question is, if we get duplicate data, how to remove those? So getting duplicate data and at least one semantics, those are two different cases. Here these are only the case where you restart. When you restart your streaming application, but you can receive from Kafka itself or some other message queue. If you get duplicate data, you just have to filter it. You have to just filter it. But this duplicate data is totally different. It is while restarting your application, it is based on your commit offset. So your first step will be read, then you will be committing, then you will be processing. Yeah, we will next see how the exactly once semantics works. Next, we will see how the exactly one semantics work. Now, the reason why exactly one semantics is not here is because because we are using two different external storage for storing data and storing offset. We are committing the offset to Kafka, and we are saving the data to Cassandra, which is two different external storage, and which are not atomic. They cannot be part of a transaction. They are not atomic here. So that's the reason somewhere in between I'm saying the crash happens. Here in between, after committing, the crash happened, or or if we take at least one semantics, after processing the data, the crash happened. So in between, some failure has happened. Only in those cases, I mean, keeping that context only, we are saying it is at least one semantics or at most one semantics. It's only during the failure, and that too between the processing of the data and committing of the data. In that case, we only achieve these errors, and because of that, we could go to at least one semantics or at most one semantics. So the reason is because we are using two different external storage, and they are not part of, I mean, they are not atomic. What do we mean by atomic? Atomic means if one fails, all fail, or let everybody succeed. If it succeeds, all the operations should succeed. If one of the operation fails, all the operation must fail. So you can think of, if if committing of offset fails, the saving of the data must also fail. Or if you see, if processing and saving of the data fails, then committing of the offset must also fail. Either both succeed or both must fail. So that's how the exactly one semantics works. So I hope you got the idea behind that. How to achieve exactly one semantics. If one fails, let both fail. In that case, you will be not committing the offset, you will not be processing the data and saving the data. So even if you are reading the data once again from the Kafka, that is okay because we haven't processed that data at all. So we'll be getting exactly one semantics in that case. That's how the exactly one. So usually you're, I mean, again, Cassandra does not support. So usually what you do here is, but again, it is not so straightforward. It's not so straightforward. You read the data, you read the data, process data, you process the data, sorry, and save to external storage. Save data as well as commit offset. You have to commit the offset here itself. Now there are multiple scenarios again here. If you are doing a lot of aggregations and saving data to multiple tables, you are saving data to multiple tables inside a Cassandra. Again, it will be tough to achieve exactly one semantics. So usually what you do is, let's say you want to do total visits from each country. Visits from each country. Let's say you are getting some raw data, and we saw the demo of total visits for each country. So you will have a country name. So we'll have count. So along with that, you also need to have offset, sorry, partition and offset. Actually, this the table should be in this fashion. So because writing a row, inserting a row to Cassandra is atomic. Inserting a row to Cassandra is atomic. Inserting, you cannot create two different tables. So you cannot have this as table 1 and the partition and offset as table 2 in Cassandra database, because Cassandra, I don't think so it supports a transaction. Meaning you cannot write to two tables as part of one transaction. I am not sure, I didn't see that happening. But let me confirm once again when let me check once again, double check it, and see that. If you see MySQL, you can write to two different tables as part of transaction. You can put inside the code, you can put your commit code inside the transaction. If one of the fails, both will fail. But such kind of transaction is not available for Cassandra. So let me showcase what I'm trying to say here. That's what, it's not so easy to get exactly one's semantics. So if you open the producer example, if you open producer example, so you can remember the path: downloads, training, Kafka examples, producer example. Just open that piece of code or project in your IntelliJ, you should get these things. So here with serialization, it's not here. Right. Consumer, if you see inside the consumer, inside the consumer code, you will see exactly once. So just for here we are making use of MySQL database. I mean, it is not a Spark application. Here I'm just trying to showcase how exactly one semantics works. So here is our consumer. It's a normal simple consumer, not a distributed consumer, a Java based consumer. So you are getting partition. So here assumption is there are three partitions. We are getting all the partitions. So here let's get offset and save. Forget all the code. We are just doing save and commit. Save and commit. So we are inserting the data to one table, and we are doing an update, just a MySQL code update offset to. So then we call both the things. This is the insert command to insert the data. This is the update command to update the table. So these two are two different tables, and we are saying insert executes. I think this is the MySQL piece of code. Execute update and execute update for both. Then we say connections dot commit. So this is how we write a transactions in MySQL. So both should be part of this transaction. Meaning when we say commit, you cannot. I mean, if one of them fails, both will fail. Writing the data to MySQL if fails, updating the offset will also fail. If updating the offset fails, inserting the data to the table will also fail. So this is how you achieve exactly one's semantics. If at all you are using a transaction based database, if you are using a transaction based database, but such Cassandra does not support such kind of transactions, so it is again a bit of a tricky thing. If you are doing multiple aggregations, you cannot achieve exactly once. What I'm trying to say here is, so you have page views, you have country visits. You have page views, you have country visits. So page views table will be having a page views table. So page is one column and count is one more column. This is our page views. We have country visits. So country is one column and count is one more column. Now from the data, we are doing both these aggregations. As soon as you get the data, you aggregate that data and do the count and keep on writing to this database. Now how do we maintain, because writing to this database is writing to the table one. This is one table, country visits table. Writing to these two tables are are independent, they are not atomic. Now in that case we cannot have exactly one semantics. How do we achieve the exactly one semantics? Somewhere something will fail. I mean, if you have if you again make partition and offset here, here again we make partition and offset here, in both the tables the partition and offset has to be updated so that we don't read it once again or we don't lose the data. But writing to this table is independent of writing to this table. Here we may do update perfectly fine, but while writing to this table we may have crashed. We might have crashed here. So which offset we will take from? Which offset we will take from? So it becomes a tricky. In that case, we have to write two different Spark applications. For each aggregation, we have to write two different Spark streaming applications. So here offset is already updated like partition 0, offset 160. Now here partition is 0. Before it could last offset was 120. So before it could update to 160, writing to this table failed. Writing to this table failed. So it was still 120. Now which offset the Spark streaming will pick from? Which offset it will pick from? How does it know that this is this is good, this is the correct offset, or this is the correct offset? I mean, usually this will be the correct offset because that's the latest offset. The lowest offset cannot be a correct offset. But if you start reading from this offset, you are failing to update. You are losing 40 messages for this table. We are losing 40. So this for this table it becomes at most once a semantics, and for this table it will become exactly one semantics. So if at all these aggregations you are doing in one Spark app. So I mean that's if you are doing multiple aggregations, again you may not be able to achieve exactly one semantics. Somewhere something will be fault. You are losing here 40 messages as you can see. So you can, I mean, I don't know whether this is an approach or not. So you have one application, so you have one more Spark app too. It will be a overkill actually just for these things. So page table we have, so it will only update the page table. So you have visits country visits table. So this Spark application will only update this. This Spark application will only update this. So in that case, it is possible to achieve country visits. I mean, achieve exactly once the semantics for each of this table. So 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 again, if you are saving the data back to Kafka, it also becomes a bit tricky. Now here we are saving the data to NoSQL database Cassandra. Again, we saw the use cases where it can be exactly one semantics, or you cannot have exactly one semantics. So let's say you are saving the data. After processing the data, you want to save the data as a separate topic. I mean you process and save data to save data here. It is possible. You will saving the data here. So here also you can commit the offset. So I haven't seen much of this commit offset. I mean to say, I did not work on this part. Whether it does, whether the saving of data and committing of offset is synchronous, I don't know. I need to check here. There is a commit async and commit sync, synchronous commit and asynchronous commit. Let me check on that. Is that saying that it will commit whenever it commits the offset the data? I mean, there is these two are part of one transaction. That I'm not sure whether these two things are part of one transaction, that I'm not sure. I think so it is 90%. I feel that it is part of one transaction. So if you're saving the data back to Kafka, so you have to save your offset also to Kafka. And I think it is part of that I need to check actually. But you got the idea, right? How tough it is to achieve exactly one semantics. Exactly one semantics. If you are doing multiple aggregations, it is not possible to do exactly one semantics. It is possible to do exactly one semantics on multiple aggregations if the underlying data store supports a transaction. So MySQL supports the transaction, so it will be a bit easy to achieve exactly one semantics. But MySQL database is not good for uh, heavy reads and writes. It is not. I mean, you cannot store a lot of data there. It is not good for huge writes or lot of data. So that is the other one more uh, totally a different limitation of MySQL. I'm not sure which all SQLs or no SQLs are supporting transactions. So in that case, you can use at least we can get exactly one the semantics. So I hope that was clear. If you're having only one aggregation in your Spark streaming, let's say like credit card fraud detection, you don't have to do more aggregations there. You have to just update one of the table. So in that case, it is possible to achieve exactly one semantics. In credit card fraud detection, you may not have to write to multiple tables. So in that case, it is possible to achieve exactly one semantics. So let's. I hope the exactly one semantics was clear. How to achieve exactly one semantics, and this is with respect to MySQL. This code is with respect to MySQL. And with respect to Cassandra, you you have to define your table in such a way that of partition and offset is part of the table. Is part of the table. We will see that code. We will see that code, but still it is not a exactly one semantics. I will just show you the code how it works. But again, based on the scenario, it could be exactly one semantics or not. But I hope that exactly one semantics was clear. Okay, I got an acknowledgement. I hope it's the same for. I assume it's the same for others as well. It's clear. I assume here it is clear for others as well. Now keeping this in mind, this is our log analysis project, which I have showcased as a demo while starting this training here. So we'll go through this code. Here we are having. I'm storing just to showcase. I'm saving the offset to Cassandra. So this is how we are saving the offset to Cassandra as well. Reading the offset from Cassandra and saving the offset to Cassandra. But still, even if I am saving the data and saving the offset to Cassandra, still it is not exactly one semantics. because we are doing multiple aggregations in this project. Hence, it cannot have exactly one semantics. But we'll showcase at least how to save the data to Cassandra, and how to commit the offset to Cassandra, and how to read the offset from Cassandra. That we will see here. So this piece of code is not there. This I recently added. This piece of code I recently added. It will not be in your image. I will share this piece of code to you. So we already know what is the use case of our log analysis. So before we go to the use case of our log analysis, so our log analysis here we are using Avro messages. Here we are using Avro serialization in fact, and we haven't discussed about the Avro serialization. We saw that we know that from the producer we have your producer here, and we have our consumer here, and this is our Kafka. So Kafka understands only in the form of bytes, so it will be sending the messages in this fashion, something like this. Because here us you will be having a serializer. Here we'll be having a deserializer. So the serializer can be a string serializer or a Avro serializer. Here the deserializer will be a string deserializer, or it could be Avro deserializer, which will deserialize the bytes to Avro objects, and this will serialize your string or Avro object to bytes. If at all you are using Avro serializer, it will serialize your Avro objects to bytes. If you are using string serializer, it will serialize your string messages to bytes, because Kafka only knows about bytes. It will take the bytes, it will send the bytes. It will receive the bytes, it will send the bytes. That's all. So it is our responsibility to do the serialization. Some serializations are already available. So here in this project we are using Avro. We are using Avro here. So for that we need to understand what is Avro file format. I think I should have taken that Avro file format earlier itself. So if you, I think you have to recall some stuffs now. You have to recall some stuffs. If you remember, we talked about the sequence files in Hadoop. So if you remember, team A, team A reads some CSV file. So we have team A. It reads some CSV file, and they save the data as a sequence file. And we also saw we have to write a sequence. I mean sales writable. If you remember, we talked about the sales writable. We have to write it. Then I said that this sequence file will be read by team B. Now team B has to, again the data will be in the form of key and value. Key could be anything. Key could be, if you remember, it could be int writable or double writable, or it could be null writable. Anything it could be. Whatever the team A has chosen. Value could also be a double writable, or it could be sales our own custom sales record writable. So if you remember, we had sales record writable as our value. Our messages were sorry, our each record was an object of sales record writable class. Sales record is a class, writable is an interface for serialization. Each record was serialized with, if you remember. So only if you have sales record writable, we can read this sequence file. So this sequence file also has to be read the way it has been serialized. If it is serialized using null writable and sales record writable, it has to be read using null writable as the key and sales record writable as the value. But I also said that how does team B will know that sales record writable is the value and null writable as the key, and also how do will they know that what all fields this sales record writable class has, what all fields it has. So they usually cannot know those things. They have to contact manually contact team A and uh, get that sales record writable Java file. So they have to get that Java file and they have to start using that code in their project and start reading the data. Start reading the data, which is not a feasible solution, because later if inside this class they add one more field. So sales record, they have a class sales record writable class, and in that class they have transaction id, customer id, item id, item value. So if team A modifies this piece of code, if they add some extra fields, if they add some extra fields, so again you have to take that code and use it here. The older code will not work. The older code will not work. They have to get the new version of the code. Again, they have to manually contact team A and explain them that our old code is not working. So then they will realize that team A that they have made some changes. They have to send those changes to team A. So which is not a feasible solution. So can we have some file format where where it is not dependent on the source side. Even if a code changes on the team A side, the older code must be able to take care of that. There need not be a manual communication between team B and team A. It has to be a bit of a generic serialization and deserialization should happen. So that's where Avro file format comes into picture. It is a generic serialization and deserialization format. You can achieve generic deserialization and deserialization. So let's see how it looks like, because we will it is it started before this. You already had thrift, serializer, and proto buffer. I think I have shared a web link. There is a thrift, serializer and protocol buffer. These already existed as a generic serializer or deserializer. This was eh, developed by Google. Now Avro is inspired from these things. Avro is inspired for these things for Hadoop ecosystem. Avro is being used for Hadoop ecosystem for generic serialization and deserialization. Now let's see how it works. So you have to go back to Spark Core project. Just reopen Spark Core project. So if you open the Spark Core project once again, so in that you will see testing folder. Inside testing folder, you will see that there is a Avro folder. I mean testing package we have. Inside that we have Avro package. So how do we read and write Avro files? So this is on RDD API. This is a RDD API. I'm just trying to explain the concept of Avro here. But we have already explained the concept. What is the problem statement it tries to solve? So this is the problem statement it tries to solve. Here we are seeing the Avro based, RDD based Avro code. For much simpler things, you can use data source API. Just like we saw read dot format dot option for CSV file, JSON file. Similarly, there exists a data source library for Avro file. Again, it is much simpler to read Avro files there. So let's see here how the things work. So what we are trying to do here is what we are trying to do here is we have our sales.csv file. We'll read this using our Spark code and we'll save it as a Avro file. That's what we are trying to do. Later, one more Spark application. We'll see how to read that CSV file. Sorry, Avro file. Here we need not be getting the code. We need not get the code from team A. So let's see how it works without getting the code from team A. How it can read the data without depending on team A. So to do that, how it works actually here is, so we have team A. Team A will create the schema file first. They will create a schema file. That schema looks like sales.avsc. There will be a .avsc file which is nothing but Avro schema file. So the team A will create this first, where the schema of your data will be available in the form of JSON. So first the team A will create this. Let's say we have our sales.avsc. So this is how it looks like. Name is Avro sales. Namespace, we have given some namespace. We'll see where this namespace and where this namespace and where this name field values are being used. We'll see that. And here we are saying that there are four fields here. Each field name is transaction ID, type is integer. Name is customer ID, type is integer. Similarly, we have name, amount paid, type as double. So we are just describing the schema of our data. So Avro requires this. And team A, whoever is saving the data, has to create this AVSE file. If you are creating a Avro file from your normal text file, you have to create a AVSE file. Now once you create that AVSE file, which is a schema file, this schema file will be taken as input to some tool. Avro tool exists. It's actually a jar file. It is a tool which is used which uses the schema and generates Java code. So the code that we had written. So if you remember, if you go back to sequence file, so we had written this code. If you remember this, sales record writable, transaction ID, customer ID, item value, and because of writable interface, these two things we get it. Writable, which writes the transaction. So this usually is written by the team A, and same code should be available for team B also. But here team A will not write the code. They will just write a schema file, and schema file, using that schema file, the code will be auto generated. It will be not written. It will be auto generated. So let's check how this code is auto generated. So downloads training. So if you go to downloads training Avro, so there we will be generating. So the way the team A works. So here I have created three different folders: code folder, a jar, and three different directories: code directories, jar directory, and schema directory. I have copied the schema here, just like a team A would have done. Team A has copied that schema here, and that jar file we have downloaded. So if you go to the jar directory, I have downloaded the jar. So it is a tool. It is called as a Avro tool. You have to just Google download Avro tools, so you can download. Just you have to say, just specify Maven. You will directly get the jar in the Maven itself, because Maven repository stores that jar. So you can see here the jar is available. Apache Avro tool. Just download this jar file. So I have also downloaded the jar file. Here is our jar. Here is a question. The question is, here I'm doing it manually. I mean, it is irrespective of SBT or Maven. Maven is a central repository. SBT can also the fetch everything from here. I mean, but but the but what's the problem here is I'm doing everything conversion auto generation of the code manually here, but you can also automate this. So that I will showcase in the log analysis project. You can automate all these steps. When you compile your code or build the project, first auto generation code generation will happen, then compilation will happen, then the jar will be built. So whenever you are creating that I will showcase when explaining the log analysis. But whatever I'm doing here, it is a manual process and usually it is not done. I'm just showcasing to explain the steps here. So we have Avro tool and we have the code. I have the code directory. I will just remove the whatever is there inside the code because the code will be generated there. So as of now, nothing is there in the code. Now, how do we generate the code from the schema? So you have to say Java that that command is not available. We just say Java hyphen hyphen jar and you use the jar file which is there in the we have jar. Inside that jar we have Avro. Then we say compile schema, specify the schema file which is there inside uh, schema folder, sales schema. Then you specify where your code has to be generated. So I want my code to be generated here. So you run this command. Okay. I always keep forgetting this. Which one is the correct option? Could not create jar operator exception. Okay, and we don't have to give hyphen hyphen I think. So as you can see here, so it took the input file as schema file and it would have generated the code. So if you go to the code folder now, as you can see here, we got something created. So you have com, data mantra, spark, testing, Avro. So if you go there, so where did we get this path? So we got this path we got this path from our namespace. So this file was created, and your path will be a package will be created in this form with the namespace. And your Java file name will be avrosales.java. So here you can see here avrosales. This is the auto-generated code. Avrosales.java. It's a auto-generated by this. So this will take care of. It will take care of. It has all these. If you see transaction ID, customer ID, member, item ID, amount paid. So you can create Avro objects here now. Using this piece of code, using this piece of code, now what happens? Now we got our code available now. We got our code. So we read our sales.csv file. We read sales.csv file. Using this code, using this code, you will have Avro object. Each record will be a Avro object. So you'll create a class object, I mean whatever class that is created, you create an object of that class. And internally it will have a serializer. It will serialize, it will get serialized into binary, because in this Java code it already has a serializer. It will serialize and save it as Avro sales.avro. You can, whatever you give the output, so the extension will be Avro. So you have your sales.avro file. So this will be, this I showed manually. Now could be automated. This could be automated. This will save while understanding the log analysis project. Now team B wants to read this. So what happens here is the schema will also be stored along with the data. So along with the data, schema will also be stored. So you have, so the schema will be part of your file itself. Schema is available here itself. You can use this schema could be used to read the data. So there are two ways to read the data. Team B can read this data. They can use sales.avsc schema file, use this schema file and generate code. They need not get the code from here, because nobody return the code. It is auto generated. So they can generate the code. Or they can use generic Avro code. I mean, Avro supports both. Using Avro, you can generate the code. Using the Avro schema, you can generate the code. Or Avro itself has a generic API to read these data, to read this data. So we'll see how the generic API looks like. How the generic API looks like. So where they just have to specify the column names, and you will get the data. You'll get the value for that column. So first we'll see how we have already seen how this Java code is generated, and this our Spark application reads. Our Spark application reads this CSV file and gives you out an RDD of Avro objects. This is our RDD you can think of. Using this code, we are we are reading the file and converting our RDD of string to RDD of Avro objects. Then finally when we save it, it will be internally taken care to serialize this as binaries. So let's see the code of how that code is being used, how that auto-generated code is being used. So this is that Avro sales.java file. So I have copied, after generating that code, we have copied it to our project file. And we have our Avro writer Spark application. This is our Spark application. So as usual, we are creating Spark conf object. As usual, we are creating Spark context. As usual, I mean, we have to also have Hadoop configuration, and we have to set the schema. Now, as I said, our data also has the schema. It does not automatically saved inside the file. We have to explicitly save the schema also. So this piece line of code takes care of that. So Avro job is a you have to import that library. So you have to import this library through your form.xml. So I have imported here. So you have to be sure that which tool you use to generate the code, version which version you use to generate the code, the same version should be used here. Higher or same version, because higher version will have the backward compatibility but not the lower version. Better to have the same version. So if you remember, my tool was here the tool that we had is 1.77 jar. So the same Avro APIs should be used. So after just import those libraries using that dependency. So then you first save the schema. First save the schema, because you will have the schema is also auto generated. This is our auto generated Java file. So here there itself it has a schema as well. So use and save the schema. As usual, we are reading the file using the text file API, our sales.csv file. We are reading our sales.csv file as usual through the text file API. We get our RDD of string. Now take that RDD of string and transform it into a key value pair. Transform into a key value pair where value we are making it as null writable, just like our sequence file. In sequence file we made key as null writable. Here value is null writable, because Avro also needs to be stored in the form of key value. It also needs to be stored in the form of key value, and our key will be our Avro sales. Will create Avro objects. This is our auto generated code. A class exists by Avro sales, so we will create an object of Avro sales, and we wrap it inside a Avro key. So what so I'll just show it here. So we have, after reading the data, we get RDD of string. So that RDD of string is transformed into a a key value pair. So we have Avro key and we have our object here, object 1. So that's how our data looks like. I have to make it a bit, because our data will be an RDD of key value pair. So you have Avro key, inside that we have our Avro object. So that is key, value is null. Avro key, Avro object 2, value is null writable, we say. Usually nothing will be there, and so on our data will be in this fashion. So this will be saved. Now how do we get this Avro object? So Avro object is generated using this generated code. So that's how the data looks like. So you can see here you have RDD of Avro key, and Avro key is wrapping the Avro sales into. Then there is no a direct API like save as sequence file or save as text file. So we have to use the internal API. We have to internal API save as new API Hadoop file. What is the output path? What is the key data type? Whatever is wrapped inside the Avro key data type, that is Avro sales. Value data type is null writable, and our file format is Avro key output file format. Just like we have text format, text output format, sequence output format, here you have Avro key output format, meaning your actual record is wrapped inside the Avro key. So it will save it as a Avro. So this is how you save the data. This is how you save the data. Only thing is we got our auto generated file by doing using some command here, but we can also automate that command. So let's run this program, and it will write the Avro. So let's see what is the input parameters we are giving here. Local, we are reading our sales.csv, and our output path that we are giving is Avro output. So let's see whether that our Avro output folder already exists. If it exists, we'll just delete that, and we'll recreate that Avro output. So let it compile, and let it run. So we will finish the reading of Avro file also, then we will wind up the session. So it is trying to write here. In a similar fashion, let's see our read, how we are reading. Are we depending on the code that is generated, or we can in generic we can write it, read it. Let it run it first. Let it run. So as you can see here, we will try to see the read code also. As usual, we are creating Spark context, and then we need the job configurations as well, Hadoop job configurations, and then we use the internal Hadoop API. Again, there is no built-in API to read the Avro file. You don't use like text file was used to read normal text file. Sequence file was used to read the binary files, but there does not exist any Avro API to read the Avro file. So you have to use the internal API. So there we are saying that our input format, it is no more a key input format. We are just saying that just Avro input format, and our record is of generic record. We don't have to say that it is of Avro sales. As I said, as I said, either you can read in a generic form, or you can auto generate the code once again using that schema file. That is also fine. This is also fine. So we are just trying to showcase this second option. So we are just saying that our record will be some generic record. Our record will be some generic record. We can also use data source API to read the, that is much more simpler. We can also use data source API to read the, because there exists a data source API to read Avro file. Just read dot format dot load. That's all. Here I'm just trying to explain the Avro concept. So you need not depend on the team A for the code changes. You can use your generic things. So you don't know what was the key here. So we are just saying your generic data, because the schema is available in the data itself. So I think it has returned the output. So if you see, this is our Avro file. So this is how the Avro file looks like. Everything is binary, but as you can see here, the schema is available here. We have transaction ID, we have customer ID, we have item ID, name, amount paid. All those things are available here itself. So whichever field you want to extract, you can just use those names and extract. So once you use this Hadoop file API, and we use generic record, and we know that we only want the key part. We don't want the value part, because value is null writable. So finally you will have RDD of generic records. So as you can see here, now we have an RDD of generic record. So from the generic record, this is your each record. This is your each record. So their API exists. I mean, you just have to get used to these APIs. Data num called get transaction ID. Whatever is value for the transaction ID. So you can access using the schema itself. Customer ID, item ID, amount paid, and you get your transaction ID, customer ID, item ID, amount paid. You can create your sales record out of that. Finally, you can do your item wise count, whatever you want to. So you have an RD of sales record. After that, we are doing our, so we actually did not depend on our source code. They may add some new fields also. There they may add a timestamp field also. A store ID can also be added. But you need not change the code here. You want only transaction ID, you want only customer ID, you want only item ID, you are only picking that. Even if some extra exists, so that doesn't change your code at all. So that's how you make a generic serializer and deserializer with the help of Avro file format. So let's run this program and check for the result. We should be able to read our Avro file and we should get the output as item wise count. So I hope you got the idea behind Avro file, Avro files or Avro serialization. Again, just search on Google. You'll get a bit more things. If you want to see, you can see in the tutorials point. But there is a better blog. There is a better blog. You can check Avro versus Thrift versus protocol buffer. So I think I had already shared this. Martin Kelpman. So this document explains in a very good fashion. This web how the serialization is done, how actually the data is stored. So those things you can get. What is the difference between protocol buffers, Avro how it is, how the data is stored inside Avro, and one more is that. So it is a good website and it will be very helpful. So it has, as you can see, this has exited with code 0. We should be okay. This is something different. Are we printing? I think it was the earlier write, Avro write, I suppose. Now we are running our Avro read. So we got our item wise count by reading the Avro file. So only thing is the way you have to read the Avro file using generic record we are using, which makes it independent of the source code. Now the same thing is being used in Kafka as well. In Kafka also the same thing Avro is being used. But we'll see those things in the next session. Slightly modified things are there in Kafka. There we have a serializer and deserializer. So there it uses Avro serializer and deserializer. For that we need some more extra things to be known. So those things we'll see as we go on with the project explanation. So let's wind up the session here and let's continue. Thanks everybody. Have a nice day and good night others. Thank you.